Hey everyone, I'm super excited to be presenting the Composer Python library from MosaicML. One of the biggest limitations in the development of deep learning-based artificial intelligence is that the learning algorithms in massive artificial neural networks are very expensive and time-consuming to run. This slows the pace of development overall and also results in the concentration of important experiments in the big labs that can afford to run them. This is also very bad because of the climate damage these experiments cause. MosaicML is a startup aiming to remedy this problem and make training of deep learning models fast and cost-effective at the algorithm level. Composer is a collection of implemented ideas in efficient deep learning. For example, ghost batch normalization uses smaller samples to compute batch normalization. This saves the unneeded computation and achieves faster and cheaper training of deep neural networks overall. Composer has several examples like this, from layer freezing, rand augment, mix-up, squeeze and excite, and many others. MosaicML has just launched Composer with a set of Google Colab notebooks that clearly illustrate how to add this to PyTorch and Hugging Face workflows. So this video will explain what's new about Composer, walking through the tutorials and method descriptions, and the video will conclude with a clip from our unreleased Weaviate podcast with MosaicML's chief scientist, Jonathan Frankle. Please consider leaving a star on the Composer GitHub repository. This is the first link in the description of this video, so please go do that, and I hope you find this video useful for working with deep learning. So we're here on MosaicML's Composer documentation page. We're going to start off by reading through the quick description, then we're going to look at the Google Colab notebooks. Personally, I love it when there are examples of how to use the new Python library or whatever you're trying to learn about. So I think hopefully the examples is a great place to get started, and then we'll walk through the different methods that have been implemented in the Composer. So right off the bat, let's read this intro. Composer is a library for training neural networks better, faster, and cheaper. It contains many state-of-the-art methods for accelerating neural network training and improving generalization, along with an optional trainer API that makes composing many different enhancements easy. So maybe we'll start with that last line, composing many different enhancements easy. The title of the tool is called the Composer, and why it's called this is because it lets you compose and chain together these different efficient deep learning algorithms because they don't intersect with each other. You can have this interaction effect, and as Jonathan describes in the podcast, it's going to be an interesting science about seeing exactly how these different regularization techniques interact with each other at scale, and different kinds of things you do, whether it's data augmentation, say label augmentation or model augmentation, these different kinds of regularization techniques. And that's why they say that it improves generalization, because these techniques like, say, stochastic path dropout, or the idea of kind of adding this like guided noise during training prevents this overfitting and improves generalization. So hopefully from this, the title of Composer is clear, and it's about, composing these different kinds of techniques together. Because, for example, you could have mix-up data augmentation, ghost batch normalization, label smoothing, layer freezing. These things, they all can, work simultaneously. So the scientists at Composer have implemented dozens of papers and trained thousands of models so you don't have to, and built strong baselines to rigorously measure their effect and measure the impact of these different techniques that are shown on the left here where the cursor is. So let's look at some of the claims. With Composer, you can build recipes to train ResNet 50 on ImageNet to the standard 76.6% top one accuracy for $40 in 1.2 hours. And this is compared with $116, so roughly 3 times, in 3.8 hours using vanilla PyTorch on AWS computing. So right there, that's a huge gain right there. 3 times reduction in time and cost. Obviously, something that's interesting. Then the next thing is train a GPT-2 125 million parameters to a standard perplexity of 24.11 for $145 in 4.5 hours. And again, comparing this with $255 in 7.8 hours on AWS. So with that said, let's get into the notebooks and see how to use this. So we'll start off with the notebooks that illustrate how to use the Composer. On the documentation page, they're shown underneath Getting Started, Installation Quick Start, Notebooks. They currently have 5 notebooks available at the time of recording this video. And so we're going to look at the Functional API, Notebook, Trainer, and NLP. So the Functional API, it looks like the most lightweight strategy to integrate the Composer functions into, say, your existing PyTorch workflows. And that's exactly what it does, is it takes the CFAR10 tutorial, the Introduction to PyTorch CFAR10 tutorial, and it adds on the Composer functions, showing you the most lightweight way to do this. Then the trainer, I imagine that using the Composer trainer, I imagine that this will probably give you better performance as you use their trainer library compared to wrapping it into your own kind of logic and that kind of thing with respect to how they really will optimize this, I imagine. But That's just my guess about that kind of API design. I'm not an expert on that kind of thing. Then we'll look at the NLP, fine-tune NLP models from Hugging Face transformers with our trainer. I think this is super fascinating, this idea of how we're sharing these model weights with the Hugging Face transformers, putting them to the model hub, and I love Hugging Face spaces, all this super exciting stuff. So I'm super excited to see how this plays together, and hopefully these things make it really clear how to use the Composer functionality. So here we are in the tutorial and using the functional API, and this is probably the easiest way to add the Composer's functions into your current PyTorch workflow. So we begin by installing MosaicML. This last little line is a neat trick to hide the output from doing the shell script to download a Python library using pip install. So we're going to be using the functional API and adding it onto the PyTorch CFAR10, like getting started with PyTorch tutorial. So this is all just taken from the original tutorial. You have the Torch Vision transforms. This is kind of how you pre-process your data. You see how you normalize it by passing in these values, and how you pass in transform equals transform, passing in this set of transforms to the CFAR10 data sets. You have the data loader, the kind of data sets and data loader, this kind of design of PyTorch with how you flow data into your model. Then you see how in PyTorch how you define these models. Here you have a convolutional layer with I think 16 filters and 16 filters to 32. Then you apply batch normalization, this average pooling to compress it. Then you have this vector representation by using torch.flatten with that intermediate tensor feature map, and then you pass it into these 3 fully connected layers to finally get the 10 predictions for CFAR10 image class labels, so like ship, deer, dog, these kind of things. So what you do in PyTorch is you write your own model training loop. So differently from Keras, where you have model.fit, you'll do things like you have your loss function, you get the predictions where you have y hat equals model x at 2 CPU, and I think it's better with moving different, like say the losses and pre-processing to GPU and CPU. And I think that's one of the big optimizations that Composer is going after, is seeing what should be done on the CPU, what should be done on the GPU, timing these things, and generally trying to make it as efficient as possible. So we have the loss function, then loss that backward, and then you call the step of the optimizer. This is a standard PyTorch kind of workflow for CFAR10. So now we're going to be adding the Composer methods with the functional API. So we import composer.functional as CF. So first, how do you add the data augmentations, the column out batch, and we'll look at the methods right after this too, or maybe we'll just look at it right now. So column out, you see how it has, column out is a data augmentation technique that drops a fraction of the rows or columns of an input image for a computer vision model. So it's going to just drop out a column or row to completely set it to 0. So it's kind of like dropout, but like a little more guided in the structure of how it's going to drop out. So this is how you add it. You have train transforms equals shared transforms. These are the original ones, and it's called shared because you're going to use these for the test set. You're not going to be applying this augmentation to the test set, and then you do it like this to get the train transforms, add it to the data loader. So this would be how you add the data augmentations implemented in Composer. So now let's look at how you implement the model augmentation. So you say model equals net. Again, net was this class that we defined up here, class net, inheriting PyTorch nn.module. You said net equals net, and then you say CF, and again, CF is the composer.functional alias. So CF that applies squeeze excite. Squeeze excite, if we come back to these definitions, squeeze excite was this really interesting layer as a part of this thing called SqueezeNet. I think the startup ended up selling to Tesla or something like that, but it's a strategy where you have kind of like this compression and expansion. I don't remember the exact details, but it's something to do with one-by-one convolutions to shrink the feature map axis on these intermediate tensors and convolutional networks. And I think the excite kind of blows it up again. And it looks like they're doing something with an attention operator also. But so this is an interesting layer in these like micro architectures back in the when neural architecture search, it still is, but it's just like more so with vision transformers these days. But squeeze and excite is one of these super interesting layers that have been around for I think a couple of years now about efficient convolutional layers. And then you add blurred pooling. So if we come back, and I think it's nice to be looking at this and coming back to it just to help cement the idea of what this is doing, you see this blur pooling. It applies this, I think it's like a Gaussian blur low pass filter or something like that to have this kind of this data augmentation in addition to the pooling. So something like that. I'm not exactly sure about all these methods, but you see how you can access them with this functional API. This methods overview, it takes you to how you do it. So you see with cut mix, You see composer.functional as CF, and then you see how you would do cf.cutMix batch if you want to just do this right in the training loop, if this is where you want to call it, or if you want to say, I think, put it into the transforms as well. So now we're looking at the notebook describing the Composer trainer. So what we do, similarly, install MosaicML, then we import Torch Vision, import Composer, Torch. We have where our data is, our normalization values, batch size, compose. We're doing the standard PyTorch to tensor, normalize with these values, and then all similar to standard kind of PyTorch. So now Composer has some models implemented. So we're using the models.cfar10.resnet56, and as we'll come to next, the Hugging Face tutorial shows you how to do a custom Composer model. So you see how in this case you do from composer.models.base import Composer model, and then you see how you say self.module equals model, and you pass it in as an argument, and this is where you put the Hugging Face transformer. So Composer model equals Composer BERT model being transformers, Hugging Face transformers dot auto model for sequence classification dot from pre-trained, BERT base uncased num labels equals 2, and then you take that and then you put it into the argument, and this is how you wrap it into a Composer model. So I think that's pretty clear, and generally I think this is super exciting, this kind of way of sharing models, reusing models with Hugging Face. So I think that's going to be a really interesting way to use Composer, is going to be to define your Composer models with the Hugging Face things. But they do also have models, especially for doing science and things like that. So they have CFAR10 ResNet56, just models.cfar10_ResNet56. Then we define the optimizer, and they're going to have all these awesome optimizers implemented in it. So that's going to be another really interesting part of it. And then with the learning rate, linear with warm-up scheduler, again, another kind of fancy technique to facilitate the optimization. And then when you have the composer.trainer.trainer, you pass these things in as arguments where you have the optimizer, the learning rate schedule, and again, that Composer model from earlier. And we saw how to wrap a Hugging Face transformer into that if that's how you want to use the Composer model. So timing it is all about doing this faster. And now we're going to add the Composer algorithms and see how that looks like with this way of doing it. So again, blur pool, we saw what that is. Call out, similar. Again, we saw that what that is. Composer.algorithms.call out, composer.algorithms.blur pool with the arguments to it if these layers require it. Progressive resizing, that's a super interesting idea to reduce the resolution of input images, and very popular in, say, some GAN architectures use this progressive growing style GAN. I think earlier it was just called like progressively growing GAN or something like that. But that idea of going from 4x8 to 8x8, 16x16 images, that really reduced the complexity of the generated image problem and so on. But so anyway, then what you do is you algorithms equals, and you construct this list of the different Composer algorithms. So you have call out, blur pool, and progressive resize. And then when we are calling our trainer again, we see how we just pass it algorithms equals algorithms. So that's how easy it is to use this within the trainer. And again, to use the custom Composer model, you see how in this example of showing how to use the pre-trained Hugging Face transformer, you see how with the Composer you need to define forward, loss, validate, metrics, and then it shows you how to do it to get like a sense of what this is. And if you're doing text classification, this is exactly how to do it. So you don't even need to change this at all, really, except for probably changing this path to where your pre-trained model is. For example, you can make an account, like mine would be Henry AI /Keros Bird is where I keep my transformer weights. But so you see how you can do this, and then again you see this is showing you how to add the tokenize function. This is all like not particular to Composer, this kind of pre-processing, unless maybe something with this. I don't think so, but maybe. Anyway, so coming back into what makes it where you come back to Composer, you see how you have the trainer, and then you see. Anyway, so I guess you would probably add this argument algorithms equals algorithms to be adding this to the BERT thing, but you see also how you get the general syntax of adding the optimizer and the learning rate. So hopefully, did I make a mistake? I might have made a mistake in saying that this was there. Oh no, never mind. So here we do have composer.optimizers linear with warm-up schedule. So Composer does have optimizers and learning rates, but I guess it's not in this tutorial as well, so that confused me a little bit. But anyway, so overall, I hope let's kind of step way out of this. So I think the functional API has shown you just cf.apply, squeeze, and excite, passing in your model as an argument, or just, adding cf dot call out, and you could even call that in the training loop when you're unpacking the next batch of xtrain. So really lightweight way to use it, this functional API. And then the trainer, I imagine it's maybe a faster way as you scale this and keep doing it, but I'm not exactly sure. But here's another way of using it with using the Composer trainer, and also seeing how to wrap a Hugging Face transformer into the Composer model object and then putting it into the Composer trainer. So I hope that was a decent overview of the notebooks, getting a sense of how to do it. So now we'll quickly look at the MosaicML methods overview. So each of these is a card in which if you click it, it describes the algorithm, gives like a picture that describes it in most of these cases, and then shows how to use it with the functional interface, the Composer trainer, and then gives some details on the implementation details, suggested hyperparameters, and more technical details about the algorithm itself. So generally these are super interesting, these algorithm cards and how they've been implemented. And this is just such an interesting thing, these little tweaks. Like what augmix is, just as an example, is this is a technique for data augmentation where you have 3 different samples from rand augment, then you do a pixel-wise averaging of the 3 different samples, then you do a pixel-wise averaging of the Frankenstein that comes out of these 3 with the original image. And it's been an effective data augmentation strategy, particularly for helping with robustness to label preserving corrupted test sets. So you see how you have these kinds of algorithms implemented. You see this list: aliB, replace attention with aliB; augmix, image preserving data augmentations; blur pool, applies blur before pooling; channels last, uses channels last memory format; call out, removes columns and rows from the images for augmentation and efficiency. And I'm not sure if you want me to read through all this, but you can check this out easily, docs.mosaicml.com, methods, and you see all the different techniques that are implemented to achieve faster and more efficient training of deep learning models. So to wrap things up, I'm going to play a clip from the unreleased WeVA podcast episode with Jonathan Frankle, in which he answers the introduction question of what is MosaicML. And quickly, I wanted to show you the publication page of Jonathan Frankle to just show what a prolific scientist he is. So Jonathan is really well known in the deep learning community for his research, the lottery ticket hypothesis, finding sparse trainable neural networks. This is really one of the most interesting papers that have been published in deep learning. But I just wanted to show this to show also just how prolific Jonathan has been in studying these kind of things around lottery tickets, pruning, different things like contrastive learning research, the expressivity of batch normalization. This paper is super interesting, training batch norm and only batch norm, and showing that you can have random features in CNNs and control it with just the scale and shift parameters of batch normalization. You see all this research in the lottery ticket hypothesis, pruning neural networks at initialization, why are we missing the mark, studying the consistency and composability of lottery ticket pruning mask, the lottery ticket hypothesis for supervised and self-supervised pre-training and computer vision models, things on the predictability of pruning across scales, trade-offs of local SGD at scale and empirical study. So I just think that, Jonathan is such a talented scientist, and, I was really had the pleasure of speaking with him about these different topics in deep learning. So I really hope you find the full podcast interesting when it's released. And overall, I'm just so excited about this company, MosaicML, and their ability to deliver on efficient deep learning implementations.
The story of MosaicML goes back almost 2 years now. And really, it started with an email from our now CEO, Naveen Rao, to me and my advisor saying, hey, nice lottery ticket paper. Want to do a startup based on that? And my first reaction, anybody's reaction who knows the lottery ticket paper well, should be, are you insane? Interesting science, not useful. And, I'm willing to admit that, this work is not practically useful. It was meant to be an exploration into understanding deep learning. But in order to use lottery ticket practically, you would need 2 things to be true. Number 1 is you need some magic way to find sparse networks early in training. The work is all about showing that these sparse networks exist, but it doesn't show an efficient way to find them. And people have been working on this problem in the literature, but in my mind, there hasn't been a ton of progress, to be completely honest. And I can say more about my thoughts on that in a moment. The other piece is that suppose you found one of these subnetworks, you need to train efficiently when you have a sparse network. And, for those who aren't familiar, just because a network has fewer parameters doesn't mean it trains faster. The network will hypothetically require fewer calculations, fewer floating point operations to be able to train. But that doesn't make it go fast because our hardware can't actually take advantage of the topology of the network. GPUs and modern TPUs and hardware like that can't take advantage of sparsity very effectively. It's used to processing, contiguous matrices or tensors or vectors. So I kind of looked at this email, getting back to the topic, I looked at this email from Naveen and went, is he nuts? Like, this is a pretty smart guy. But we got to talking, my advisor and I sat down and talked to him, and, Hanlin Tang, his colleague from from his Nirvana days, also joined now our CTO. And we came to the following conclusion. There's a lot of opportunity to improve neural network training by making the training algorithm more efficient. And what I mean by algorithm is the following, because it's worth clarifying here. So there are a lot of ways that you can make training more efficient. One is you can build a faster chip. Like NVIDIA just released the H100. It's a lot faster than the A100, which is a lot faster than the V100. That makes training more efficient and cheaper. Another thing you can do is write better compilers. You can take the same set of operations and run them more efficiently. These are things like CUDNN and kernels and Triton and that sort of thing. But I think the interesting observation here is all of this is taking the exact same math, the exact same way of training, every operation that you're doing, and just finding ways to run it faster. You can, spin the GPU faster. You can have, faster tensor cores. You can, pick the right operations to run it faster. But it's still the same math. You'll get exactly the same weights in the network, assuming, non-determinism doesn't kick in on the GPU or things like that. And the lottery ticket work is interesting because it says, actually, we can change the math. We can get you a different network than you would have gotten otherwise, but it's just as good. And hypothetically, in our fantasy land where we can accelerate sparsity, it would have been more efficient to get there. We can change the algorithm to make it more efficient. And that's what Mosaic is built on, is trying to look at ways that change the math, that fundamentally change the training algorithm to make things more efficient. And I'll give you two reasons why this, makes a lot of sense to me intuitively. One is that, think about the math behind deep learning. There's nothing correct about this. It's not like we're doing the right thing and Mosaic is doing the wrong thing, but making it work. We're using SGD, which is a convex optimization strategy in a non-convex landscape. If you want to get that network to train, you need like all the right hyperparameters just the right way. If you set the learning rate a little bit too high or low, bad performance. You need batch norm or layer norm or pick your norm. You just like, we're living in this tiny, tiny space of networks that work well. It's minuscule. It's like, you step off of this tiny little island of stability and you fall into lava and your network doesn't work very well. So, there's nothing correct about what we're doing, so we shouldn't be afraid of changing the math. The other reason why I think this makes sense is look at this tiny space of networks. We don't know how to describe this tiny space theoretically. I can't give you a proof or a statement or a set of assumptions to describe it. And I think of this the analogy I like to use is biology. So imagine we have the laws of physics. Think of that as all the neural networks that are out there. We could describe them all. Think about biology in, the real world. This is one emergent property of physics. We are just physics. This is one outcome of the laws of physics. If I gave you the laws of physics, you would never predict the biology here on Earth, partially because it's one very small possibility in the range of a huge number of possibilities, partially because it's so complex that from first principles, it would be hard to predict. I look at the neural networks we train in practice kind of metaphorically like this biology. These are highly complex systems that have emerged from very simple dynamics like physics, but it's one specific thing that might have emerged. And we can imagine all sorts of possibilities. In theory, we have to contend with all these. But in practice, we only deal with a tiny portion of them. And when we study biology, we don't go down to the physics immediately. We look at motifs and systems and behaviors and mechanisms and all these higher level abstractions, things that we wouldn't necessarily think of from first principles in physics. And so I think of this in the same way as deep learning. I don't care what might happen. I don't care what you can prove. I care about what is happening and how to describe it. Even if the descriptions aren't perfect, I don't need a proof. I just need good empiricism. And then you can think of what we're doing as almost like pharmaceuticals. We're designing some kind of chemical or some kind of intervention that takes advantage of processes we understand to get a different behavior out of the system. And so we design a lot of these interventions. Lottery ticket is one of those. Your body chemistry is no longer functioning the way it was before, but ideally you'll get to a similar place, or you'll be, just as healthy as you were before. But, ideally we can make that outcome happen in some desirable way. And, I'll continue this metaphor for one more moment. One of the big challenges is not just, designing one pharmaceutical. You need a lot of pharmaceuticals to treat different conditions or to address different aspects. And, lottery ticket you can think of as one pharmaceutical. At Mosaic, we have, I think 25 and counting right now. And that and counting is because we've got a lot more in the pipeline that you'll expect shortly. And the last thing I'll say here is if I handed you 25 pharmaceuticals, you wouldn't take them all. You wouldn't just pop all the pills into your mouth and say, I will be better now. These drugs can interact in really dangerous ways. And so a lot of the magic of our work is trying to understand the science of how do these things interact, what's going on under the hood in these networks that causes things to interact negatively. Some of this is systems optimization. Some of this is, just two methods seem to over-regularize or what have you. But there's a science here that we're starting to uncover, and that helps us build recipes. So I'll stop there. I'm rambling. But really, Mosaic, improving training algorithmically, I think this is a new layer of the stack. And I think this composes really nicely with what lots of other folks are doing at other layers of the stack, hardware, compilers, all the way up to good, UX and ML ops. So, that's where we are.